visible spectroscopy. So, what is visible spectroscopy? It is an analytical technique that uses the interaction of visible light to measure how much a substance can absorb or transmit light in the electromagnetic spectrum, which is just a long range of radiation with two extremes, with that being radio waves and gamma rays, but we're more looking at the visible light part of it. So it has multiple uses in certain fields such as pharmaceuticals, biochemistry, environmental monitoring and material science. And some examples include analyzing biomolecules and monitoring reactions, which could be an enzyme in a system which could cause a color shift, and that could be recorded to see what's happening. So the first method, we calibrated 7 ink colors, and that was done with a spectrometer, which is seen in the top right. And when we calibrated the 7 colors, we had to check for the maximum absorbance of the ink, since this is the most sensitive area and therefore the most precise, as less error can occur. And the results can show how each separate color has its own attributes, and which makes it identifiable. And going back to the enzyme example, that can show you what color it is changed into or shifted into, and what can happen from that. And 2 examples I have chosen are green, which has an absorption peak of 628.3 nanometers, and this is because it mostly absorbs the red light, and so the green light is reflected back outwards. And that is also the reason why leaves are green, in a nutshell. And red, which has an absorption peak of 520.3 nanometers, and this is simply due to it being able to absorb red light. And these are the 2 examples. So for the second method, we had to test the max absorbance of 6 separate cordial dilutions, which were lime cordial, and that varied from 20% to 100%, which is also called undiluted lime cordial. And the absorbance measured showed that the less diluted the cordial, the higher the absorbance is, as shown in the bottom right hand corner. And this shows the final analysis, and this spectra is from a company called Unchained Labs, and this shows how similar they can be, because despite this being a DNA dilution series, the peaks overlap each other. So I'm pretty certain the 2 peaks on the top right one that are in the center are anomalies caused by either bubbles or fingerprints. Now the Beer-Lampert law is very important, and it has the equation of A equals epsilon Cl, and this is important since the calculations required are grounded within this equation. However, on the next slide, we have a calibration curve, and so we have a line equation which allows us to insert a unknown absorbance into it to get a concentration, which is shown here. So the unknown cordial was calibrated 3 times, and it had the peak of 0.188 absorption. So after the initial 6, which was the 20% to 100%, they were inserted onto a scatter graph and came out with the equation of y equals 0.0105x minus 0.102, which is shown on this graph, and that's the unknown recorded. Now then, with this line equation, we can insert the unknown into this, which gives us 0.188x minus negative 0.102 divided by 0.0105, which gave us a concentration of 27.6%, which is our final concentration of the cordial. And so, with it being measured 3 times, and its absorbance being 0.188, it proves that Beer's law is valid and grounded within spectroscopy, since it was within the range of the calibration curve. However, there most certainly was errors, as seen before, which are human fingerprints on the cuvette, air bubbles in the cuvette, and an instrumental drift. And these 3 can cause it because human fingerprints will interfere with the light, and the air bubbles will reflect the light back onto itself, and into a solution, which could cause peaks that are unneeded. And an instrumental drift could just mean there was too little or too much added into the cuvettes. So, with the experiment being concluded, it has shown how visible spectroscopy has found out this unknown concentration of the lime cordial, and it has also proved that different colours within the spectrum have different max absorptions and wavelengths, which allows them to be verified on what they are. And so different substances can be detected easily, and due to it being precise, it is used in certain areas and industries. And this experiment has also proved the Beer-Lampert law, and so has proved that the absorbance is linear with the concentration. These are my references. They are very useful, and that is the experiment.